tested out of trig, except for two of you that took the course, I don't feel like there's a real need for me to do some of the problems in chapter 6. So I want to get to the good stuff as soon as I can. We basically have 2 chapters left to do, and they're the most difficult. So I'm going to try and go slow through these last 2 chapters, okay? I know it's a little weird to have some new material come in before the next test, and I understand that. I hated that myself as a student. But this stuff that I do today should really be a review, okay? So I don't think it's going to hurt you at all. And I mean, there's in this first section, there's barely any problems to do, and next section, things should be easy for the first few sections of chapter 6, and that's all I'm going to get to today. So I want to start with 6.1. So this is trigonometry. Oops. So what does that word mean? What does the word even mean? I'll try and do three pieces of it. Oh, Jace, you are here. Did you just get here? Were you here already? You were on the break. I'm sorry. Right? Losing my mind. What's try mean? 3. Gnomes are vertices or corners, right? Or angles. And then what's a metric? Measure. So this is measuring the 3 angles of a triangle, right? So what's interesting is, well, we start with a right triangle, right? So a right triangle. We're eventually going to move to any triangle, but for now it's right triangle. And I want to call this base angle theta, and of course there's a right angle there, right? So this particular angle is called theta. And of course this square box is signifying right angle, right? 90 degrees, yes? Yeah, we okay here? So usually what we're trying to do is superimpose this triangle in the XY axis, okay, with theta being at the origin, and the top vertex being a point on the circle. Les. Especially interesting when the circle is of what size radius? What? Not pi. What? Not 2. Almost 2. 1. Called the unit circle. Have you heard this before? Who's heard that before? You better have heard it before if you already passed out of trig, right? Unit circle, a radius of 1. So you can see here what part of the triangle is the radius. Hypotenuse. So what I'm always going to be thinking about is that hypotenuse is the radius of a circle. And when the radius is 1, everything is as simple as possible. So I like this idea, and let me just create this real quickly with something called Sketchpad. I used to teach high school geometry all with computers, and we use this program. It's expensive. Desmos GeoGebra does a pretty good version of it. So if you ever want to play around with something like this, GeoGebra is where you would go with it. But I want to take a look. I'm going to create my grid here. There's my XY plane. The radius would be 1, yes. Yeah, which is also the hypotenuse. So I want to create a circle here of radius 1. And I want to create a point on the circle. And to each of my axes, I'm going to create a perpendicular. Oh, no, I'm sorry. I want a parallel to my y-axis. There's nothing for you to do here. Just listen, kind of, right? And I want my hypotenuse, my height of my triangle, and my base of the triangle. I'm going to color in the triangle just for the heck of it. And you can see I'm looking at all of these triangles. That's what my trig is going to be based on. This particular right angle triangle embedded into a circle, right, where the hypotenuse is the radius of the circle. Okay? When my angle opens this way, I'll say theta is positive. When it goes this way, I'll say theta is negative. So if I'm going around the circle clockwise, I have a positive angle. If I'm going around counterclockwise, I have a negative angle. So from my x-axis to my hypotenuse, I'll say theta is positive. It's just the angle, right? You with me there? And if I move the other way around the circle, this way, we'll say theta is negative. And theta is just the Greek letter, right? So it's like pi. Pi is a Greek letter, but we call it a particular number. Theta is a Greek letter. We call it the measure of the angle. Sina, I don't have a recording for Monday because I didn't feel good. I went over the things I wanted you to do, and right? So. Nice. How do we measure angles? How do we measure angles? Radians? You say radians? Yeah, that's beautiful. Most of us just remember from high school degrees, right? But we want to move toward radians. So most of your 098 course, if you took it here, was in degrees, and then they start to convert you over to radians. But how many degrees are there in a circle? 360 degrees. What about if the circle's bigger? Still 360, right? Right? So why 360? It's from ancient Egypt. The Egyptians figured out how many days a year. How many days a year in the Egyptian calendar? 365. They were off by a quarter of a day, right? 365 days in a year is 365 and a quarter. That's a leap year thing, right? So, but they had five gods, right? The ancient Egyptians had five main gods. They had more than that, but five main gods. Each god got a day for just a huge party every year. So what they called the whole cycle was 360. And that's where we got our 360 degrees from. It's also kind of nice. I mean, they were brilliant mathematicians, but that 360 divides by so many numbers, right? Divides by 2, divides by 4, divides by 5, divides by 9, divides by 10. So it's really a perfect little machine that they created here for thinking about a circle. So the size of the circle doesn't matter, okay? Any size circle, but we're going to try and use a circle of radius 1, the unit circle, most of the time, because everything's easier to understand in that case. Okay? So, but what is a radian? Well, what is it related to? The radius. So what I'm going to do is I'm going to take this radius of my circle, right? Take the radius, and I want to bend it along the arc of my circle, right? So bent radius. And what I'm going to do is I'm going to lie that radius on my circle. How many times does it hit? More than 6. Nope, less than 12. How many radii fit around the circle? Anybody know? Not 2. It's bigger than 6. 2 pi times. So a radian is this bent radius that will measure how many times it will go around the circle. And of course, we get the 2 pi from the circumference, right? Do you see that circumference is 2 pi r? Right? So that r is almost a variable because one radius of a small circle is not the same as the radius of a big circle. But again, since same thing as the circle has 360 degrees, no matter what size it is, the radian fits around 2 pi times, no matter what size the circle is as well. So our first thing that we have to do in 6.1 is to be able to convert degrees to radians and vice versa. So if we look at just something like 30 degrees, and again, we're always talking about a right triangle. What is it? Yes, yes, yes. But it's a pi over 6. So first of all, if I know that 2 pi r is equal to 360 degrees, right? Yes, you with me? Then I know my radian is the same as 360 degrees over 2 pi. So what is that? 180 over pi, right? So 180 over pi is my conversion factor. So 180 over pi, or pi over 180, is the converter. So if I have 30 degrees, which one do I want to use? Remember, I want to convert this. I don't want it to be degrees anymore. I want degrees to cancel. Okay? So this is 180 degrees over pi radians, right? Or pi radians over 180 degrees. So which one do I want to use, the first one or the second one, to cancel my degrees? The second one. So I have pi radians over 180. By the way, these guys are equal to each other, right? So what number is this? (180 degrees over pi). What number is that? 180 degrees is half the circle, right? The whole circle is 2 pi, yes? So what's 180 over pi? 1. Half the circle over half the circle. So I'm just multiplying this by 1. What do I get? 60, right? So 6, I mean, right? Pi over 6. The degrees cancel, right? 30 over 180 is 6. So this is it, pi over 6 radians. Whenever I'm converting degrees to radians, I multiply by pi radians over 180. We want to kind of create our degrees, radians chart here. And we're going to start with 0. Of course, that's 0 radians. We're going to go to 30 degrees. That's pi over 6 radians. When I don't write radians, I'm assuming it's radians. If I want degrees, I must put the degree symbol. If I don't write anything, it's radians. If I have a degree symbol, it's a degrees. Let's do 45 degrees next. Convert that for me. So I'm going to multiply by what? Pi radians over 180 degrees, right? What cancels? The degrees. And 45 into 45 twice is 90, right? So this is pi over 4 radians. The next guy is 60. And then 90. So what's 60? Can you do it in your head yet? Pi over 3. And what's 90 degrees? Pi over what? Yes. This thing should be on your formula sheet. Of course, I'm going to ask you possibly to convert negative 240 degrees to radians. John, you all right? I did tell you to take extra Advil today, didn't I? I said it's a pretty harsh lesson today, right? So not this Monday coming because we're going to review, but the Monday after it, probably the rest of the semester, 500 milligrams of pain reliever will do you some justice. Let's convert negative 240 degrees to radians. So I'm going to take my negative 240 degrees and I'm going to multiply by my converter. I'm going to actually just multiply by 1, right? Pi radians over 180 degrees. Remember, this thing is, in terms of my circle, right? I'm going all the way over to here, right? There's my theta. It's negative, so I'm going counterclockwise. But wait, which way am I going? Clockwise or counterclockwise? That's clockwise, right? Right? The hands on the, yes. Sorry about that. Good, so the degrees cancel. I'm still going to keep my negative, but I'm going to get, what, 24 over 18? Pi radians. What goes into both of those? 6? Yeah? So minus 4/3 pi radians. Yep, 6 into 24 is 4, and 6 into 18 is 3, right? Nice. Let's convert radians to degrees. So, for example, 7 pi over 6. Again, if I don't say radians, it's automatically radians. Okay? So, I don't have to have the word radians in there. We'd rather just kind of recognize that if it's not in degrees, it's in radians. I want you to be able to draw these pictures. And so what I'm thinking of is what's called the reference angle. This is my reference angle. And so what I'm saying is I'm going to cut pi into 6. So I'm cutting the top half into 6. Right? The whole thing is 2 pi, so cutting pi into 6 is the same as cutting the whole circle into 12. Right? So there's my whole circle into 12. But I want to look at what's the reference angle is this particular one right here. This guy is my reference angle. There's my pi over 6. And so I'm going to start counting. 1, 2, 3, 4, 5, 6, 7. There's my pi. There's my 7 pi over 6 right here. And it's a right triangle. That'll make a little bit more sense later. Let's convert it. So this is equal to 7 pi over 6 times 180 degrees over pi. Again, it's understood to be radians, but do you see what cancels here? The pi's cancel, right? The pi's cancel. The 6 goes into 180 30 times, yes? So it's 210 degrees. How are we doing? We okay? So the first thing you're doing in the textbook is problems in, just do all these conversions for me. Find it in a second, sorry. Why is it so blurry? Numbers 23 to 45. Oh no. Yeah. 23 to 45. Convert from degrees to radians, radians to degrees. 24 to 35. Nice. Ready? 6.2. Yes? Question? Yeah. Negative. Yeah, do one with negative degrees. Sure. Let's do minus 90 degrees. So we know our circle in the x-axis. Every time we move on the circle to one axis to the other, it's 90 degrees, right? So this angle right here is negative 90 degrees. Right, 90 degrees is our perpendicular thing, right? And you can kind of see that I have 2 pi over how many sections here? How many sections do you see in the circle here? 4. So it's going to be the whole circle over 4, right? But let's use the conversion here. So negative 90 degrees times pi over 180 degrees. The negative is going to stick around, so it's minus pi over 2. Again, I don't have radians written down there, so we assume it's radians. What the hell are radians again? It's the number of times I take the circle, no matter what size it is. I grab the radius, I bend it. It's the number of times I can fit, right, that radius around the circle. Each one of those is a radian. Each one of those radii that I bent is a radian. Here we go, 6.2. Well, it turns out that the size of the circle doesn't matter whether I'm talking about degrees or whether I'm talking about radians, right? What's different about them is that the radius is a different size. So I like to think of this as a variable ruler. How many of you have taken statistics? Statistics. Only Brian. Have you ever heard of a standard deviation? Has anybody heard of a standard deviation? Standard deviation measures how much your data is spread out. But for every set of data, it's a different number. But it does the same thing. And so this is like a variable measuring kit or tool, right? Right? So for some circles, a ruler is 12 inches. For others, it's a different size, that kind of thing, right? So standard deviation is a lot like a radian. It's a variable measuring stick. So, but what happens is, so if I have my 2 circles of different sizes, and I draw my right triangle, I draw my right triangle with the radius, right, and there's theta, and I have right triangle here and a right triangle here, right? I don't need the rest of that black piece. I'm writing it probably because I want to see that. I want to see the hypotenuse is the radius and the other piece is the radius. It turns out that there's something pretty unique about both of these triangles that make it so special that we give it a name. Does anybody know the names we're going to start to talk about? We're going to talk cosine and tangent. Has anybody heard those before? Sine, cosine, and tangent, yes? What are they? Yeah, they're ratios of sides. So I'm on Sketchpad again, okay? And I'm going to extend my base. I'm going to extend my hypotenuse, and I'm going to pick some new hypotenuse here and create a perpendicular down to here. So now you can see I have two triangles, two right triangles, embedded with the circle centers at the origin, right? And on each hypotenuse is the radius of the circle. So I'm going to finish off these two sides, and these two sides. And I'm just going to hide a bunch of stuff. So angles theta. Notice the theta is the same for both triangles, right? No matter how I change the triangles, whether I change it smaller or larger, the theta is still the same for both triangles, right? We agree? Theta is the same for both triangles. So I want to look at the ratio. Well, maybe I'll measure my angle here. So measure angle. There it is. Theta is 48.3. And I want to measure the opposite side divided by the hypotenuse. So I want to measure that ratio. I want to do the same for the big triangle. I clicked on the opposite side of the angle, the side furthest away from the angle, right? And the hypotenuse, and I measure ratio. And no matter where I change, those ratios are the same. And since it doesn't matter what size the triangle is, doesn't matter what size the circle is, doesn't matter the size of the radius, all that matters is the angle. And so since that's always the same, we came up with a name for it, and that's sine of theta. So we've got a right triangle with an base angle theta. This side I'm going to call the opposite side. It's the furthest away from the angle. This one is the hypotenuse. If you have never seen Key and Peele before, there's a scene of them as friends in high school in a geometry class, and the teacher's teaching geometry, and then I forget which one it was. Keegan Mike, yeah, Key. No, Jordan Peele, is it? Yeah. So Keegan goes, "I wish I was high on hypotenuse." And I don't know. Watch it. Just go look at the hypotenuse joke in Key and Peele. Okay, and this side we call adjacent. So you'll often see it labeled like this: OPP, ADJ, HYP. And so we just looked at the opposite over hypotenuse ratio, right? How many sides are there here? 3. If I pick 2 of them, how many combinations is that? 3 choose 2. Does anybody know probability? How many combinations is it if I pick 2 of the sides? 6. So we actually have 6 trig functions: the sine, the cosine, the tangent, the cosecant, the secant, and the cotangent. Because when I'm picking 2 sides out of 3, I could pick opposite over hypotenuse or hypotenuse over opposite. So this particular one, first thing we're going to remember is SOHCAHTOA. And that is saying sine of theta is the ratio of the opposite over the hypotenuse sides. Cosine of theta is the adjacent over the hypotenuse. And tangent of theta is the opposite over the adjacent. We're memorizing this, of course, it's going on our formula sheet. Sine of theta is the opposite ratio of the opposite side divided by the hypotenuse. Cosine is the adjacent divided by hypotenuse. Tangent is opposite over adjacent. SOHCAHTOA. Okay? SOHCAHTOA. We have these reciprocal trigs. And so cosecant theta is hypotenuse over opposite. Secant of theta is hypotenuse over adjacent. Cotangent of theta is adjacent over hypotenuse. I'm sorry, over opposite. So we just remember these three with SOHCAHTOA, and then the other three are the upside down, right? The reciprocals. Tangent and cotangent are so easy to, they sound so much alike. I know they're reciprocal to each other. COS and SOC is kind of what I see here. Cosine and the secant are reciprocals. And then the other one I could never remember, but I knew it was the last one. So sine and cosecant are reciprocals. Sorry, my parking just expired. Nice. A lot of this sound familiar to everyone? Yeah. So, what we have to talk about is this in terms of x and y. We have to talk about all these trigs in terms of x and y. So what we do is we take a unit circle, which is a circle of radius 1, and we take a look at our triangle. Now my radius is 1. I'm going to call the height y, and I'm going to call the base x. So what happens to sine now? We already know that sine of theta is opposite over hypotenuse, which means it's y over what? 1. So what I'd really like you to think of is the sine function as the height of that triangle. The sine function as the height of the triangle, right? If I'm looking at Sketchpad here, and if I look at the height of the triangle, look at just that yellow triangle. What's the max height it goes to? Look at the yellow triangle. So when I start at an angle of 0, what's the height of the triangle? Well, it's not even a triangle, but it's 0, right? And as I move around the circle, what's the height of the triangle going to? 1. And then what? Going back down to where? What height? 0. And then down to what height? -1. And so it's weird a little bit to think of a height as negative, but it just means down, right? And so if sine is the height, we really have to be thinking about all students take calculus, or all school teachers curse. I like to also say all students take calculus provided they pass pre-cal. What am I saying? All of the trigs are positive in the first quadrant. What's the only trig that's positive in the second quadrant? Guess. Sine. Sine is a height. Aren't the y values in the first quadrant positive? What about the second quadrant? What about the heights? Positive. What about the heights over here? If I draw this triangle, what about that height? Is that positive? That's negative. So sine is not listed there as positive. All students take calculus. That means our cosine curve is really what? Adjacent over hypotenuse, which is what? X over 1, or just x. So when I'm thinking about cosines, I want to be thinking about the width of the triangle. How wide is it? And tangents are what? Nice, y over x, which is what? Nice, that's the slope of what? Yes, slope of the hypotenuse. When I draw my triangle in this quadrant, what kind of slope do I have here for the hypotenuse? Positive or negative? Positive. All trigs are positive in quadrant 1. When I draw my triangle over here, now what's the slope? Positive or negative? It's negative, right? Can you see the letter N there? Negative. So only sine is positive in the second quadrant, which means tangent is negative. Tangent down here, again, positive slope. Triangle over here, negative slope, right? Nice. We got to look at a couple of values for our trigs. And of course, we can do all of these on the calculator, and we will, but I want you to have this memorized. Of course, you'll put it on your formula sheet. So what we're talking about today are reference angles. For now, we're going to do them in degrees and radians, but most of the time we're going to only be using radians. So I want to look at theta, sine of theta, cos of theta, tan of theta. And my reference angles are all in quadrant 1, and we did them before: 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Our radian version is 0 radians, pi over 6, pi over 4, pi over 3, pi over 2. And again, that's what we prefer to use in this course, okay? If you took your 098 course, you used degrees quite a bit. High school geometry degrees, right? So you're going to memorize this pattern, and by the time I'm to the last row here, you should be able to say it with me. So here we go. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of, wow, great energy, square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. These simplify to 0, 1/2, can't be simplified, and to 1. The cosine function moves in the opposite direction. If you think about it, as the height of the triangle gets bigger, the base gets smaller. So the cosine function, I'm just going to take the same values and put them in opposite order. 1, square root of 3 over 2, square root of 2 over 2, 1/2, and 0. Tangent of theta is y over x, which means it's also sine over cosine. right? Because sine is like a y value, cosine is an x value. So what I need to do to get the tangent of theta is divide my sine value by my cosine value. So what's 0 divided by 1? 0, right? What's 1/2 divided by square root of 3 over 2? That's 1/2 times 2 over square root of 3, or 1 over square root of 3, which is the same as rad 3 over 3. 1 over square root of 3 is 1 over square root of 3 times 1. And when I rationalize, I'm going to take my irrational number in the denominator and multiply by that number over itself. So notice that rad 3 over 3 is 1. Upstairs I get rad 3, downstairs I get the square root of 9, so I get rad 3 over 3. So what I'm saying is tangent of pi over 6 is rad 3 over 3. Watch that on Desmos. Don't let me go too fast here. I think I might have just lost a couple of you. Almost done today. So tangent of pi over 6 is the decimal 0.57735, etc. And notice that square root of 3 over 3 is the same decimal. So this is a nice kind of way for you, if you forget that table. There's no way you should forget the table. It's too easy. But you can double check things on Desmos, knowing what some of these ratios should be. I know it's mentally challenged to sit here and do this for this long, but you should be taking notes. If you're not taking notes, you're not getting the stuff in your brain another way. You need to get it in your brain every way you can. You have to hear it, you have to see it, you have to write it. You got to do it every way. If you know it already, great. Then I'll shut up. I want to finish my table here. This is my reference angle table. I have to do a sine divided by cosine to get tangent. What's square root of 2 over 2 divided by itself? 1. What's rad 3 over 2 divided by 1/2? The denominators cancel. It's just rad 3. And 1 divided by 0 is trouble. We call it undefined for now. When you take calculus, you'll learn what it really is. I need to show you where these come from. But the pattern is easy, right? You have it, right, already? Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. It's really that easy. You won't even need to put it on your reference table if you just think about it a little bit, right, on your cheat sheet. So these come from these special right triangles. And there's really just two of them. From the square, we have, what kind of triangle is this? Do you remember? Isosceles triangle, yes? Which means the base angles are congruent, and that means also the sides are congruent. So this would be side X and this would be side X. How can we find the hypotenuse, side C? Yep, Pythagorean theorem, right? X squared plus X squared should equal C squared. Everybody with me there? A squared, right? If triangle ABC is a right triangle, then A squared plus B squared is C squared, right? Named after Pythagoras because he stole it from the ancient Egyptians. They knew of it, but there was no found proof of it. Doesn't mean it wasn't. They didn't have it. Right when the Romans basically looted ancient Egypt, it was proven in China, and it was proven in China in some 2,000 years before Pythagoras. So, but he's the one who published it, so to speak. So he got his name put on it. So what do I get? How many x squareds on the left? Yep, 2x squared is equal to c squared. So c must be the square root of 2x squared, or better yet, x rad 2. The 2 can't come out of the square root, but x squared is a square, right? So I can get the square root of x squared is x. So now look at our triangle again. Oops, sorry. I want to try and draw an isosceles. And I know my sides are x, x, and x rad 2. What are my angles? Yeah, 45 degrees each. So the sine of 45 degrees, which is the same as the sine of pi over 4 radians, is equal opposite over hypotenuse, which is x over x rad 2. Everybody with me here? I know you're at your wit's end, but you gotta hang with me here. You gotta know this stuff. You got to know this stuff all the way through your math education. If you're engineers, you got to know this stuff by heart instantly in differential equations 4 semesters from now. If you're in Calc 2 and you can't do this trig, you will never pass Calc 2. In 2 semesters from now, I'm talking another 2, not this one, another 2, you have to know this trig stuff. So what cancels here? X's. I get 1 over square root of 2, and I'm going to rationalize that. Again, 1 over square root of 2 is 1 over square root of 2 times 1, and the version of 1 I'm going to use is rad 2 over itself. And so I get square root of 2 over square root of 4, which is square root of 2 over 4. Square root of 0 over 2. Sorry, square root of 2 over 2, right? Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2. There it is, my 45 degree, my pi over 4 reference angle. So it also makes sense that cosine of pi over 4 is the same, right? Yeah? You agree with that? Because the opposite and the adjacent sides are the same. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. My next special right triangle, can you handle this? Can you handle another 15, 20 minutes? If you need to go get something to drink or something, go ahead. Right? But I am recording it, but I want you there with me while I'm doing it. I know it's painful. We'll start doing problems soon. I need this stuff known. It should mostly feel like a review. Does it feel like a review to anybody? My next special right triangle is the 30, 60, 90. And I'm going to get that from my equilateral triangle. What we do is we draw a perpendicular. So we knew the angles were all originally 60s, right? So now we got a 60 here, we've got a 90 here, and that means this one's got to be what? 30, right? Because all the angles add up to 180, right? You remember that from high school geometry? All the angles of a triangle add up to 180. So if my hypotenuse, if the side of the triangle was x, was 2x, then when I cut it in half here, right, the basis of this triangle is now x, and I have to find side B. So what do I get? X squared plus b squared equals 4x squared, right? I square each side, right? X squared plus b squared is c squared. So 2x times itself is 4x squared. So b squared must be 4x squared minus x squared. So b squared must be 3x squared, and b must be x rad 3. So looking at my 60-degree angle, and I have an x rad 3 here, and I have a 2x here, and I have an x here. What trig do you want to do? Let's do a tangent. Tangent of 60 degrees is the same as tangent of pi over 6. Nope, sorry, pi over 3, right? Is x rad 3 over x. It's opposite side over adjacent side, which is just rad 3. Right there, right? Yeah? Tangent of pi over 3 is rad 3. Imagine I put my 30-degree angle down here. Again, this is 2x, this is x rad 3. What about the cosine of 30 degrees? That's the same as the cosine of pi over, help me, pi over what? $30 is pi over 6, right? Yes? It's x rad 3 over 2x, right? Adjacent over hypotenuse. So adjacent meaning the side touching the angle. That's not the hypotenuse, over the hypotenuse. So what cancels there is the x's, and I get rad 3 over 2. On Desmos, cosine of pi over 6, right? And that should be the same as rad 3 over 2. There it is. Nice little way to use a calculator to double check your ratios. Last Last piece. I promise. Yeah, go back to here. Yeah. Yep. So this is I actually wrote this on the wrong screen, but do you need do you need I think you need the 30 60 90 maybe? No? You okay? Okay. All right, last thing today, promise. What time is it? I mean, it's an incredibly long class. I don't know how anyone could go the whole 2 hours and 35 minutes. I don't. It's not possible humanly. But here we go. Reference angles. We need to know a couple of things. We need to know our quadrants: quadrant 1, quadrant 2, quadrant 3, quadrant 4. We need to know all students take calculus provided that they pass pre-calculus. And again, for the few of you that don't have to take calculus, I tried to warn you at the beginning of the semester, but it's okay. You can make it. Calc 1 is so much easier than this class. So much easier. Calc 2 is more difficult than this class. It depends on what you're studying. So if you're going computer science route, if you're biochem, you're done after Calc 2. Yeah, okay. Thank God. I need to know my reference angles, how it chops up the slice pizza, right? So I have 3 of them. I have a pi over 6, I have a pi over 4, and I have a pi over 3. So when I'm cutting pi into 6, that means I'm cutting the whole pizza into 12. And I'm interested in only the reference angles. Those 4. I call them the bow ties. So notice what I get there. I get a 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. 6 pi over 6, 7 pi over 6, 8, 9, 10, 11 pi over 6. Notice that all of the other ones, like this one, 2 pi over 6, reduces. Right? You see that? All of the other ones reduce. So they are not a reference angle of pi over 6. Only the bow tie ones, only the pieces that create the right triangle with the x-axis are the ones we want to be looking at. For pi over 4, I'm cutting the pizza into pi into 4, which means the whole pizza into 8. So I've got a 1 pi over 4. What's next? 2 pi over 4 reduces. Then a 3 pi over 4 doesn't reduce. That's my reference angle. 4 pi over 4 reduces. 5 pi over 4 doesn't reduce. 6, 7 pi over 4. Again, the only ones I want are going to create this bow tie kind of look with the x-axis. Pi over 3 is a weird one because I don't want to draw like a y-axis. I want to cut pi into 3, so the whole thing into 6. So I've got a pi over 3, I've got a 2 pi over 3, I've got a 4 pi over 3, and a 5 pi over 3. Even if you took high school trig, or you took our 098, or you just remember trig, whatever, you'll what was I going to say? You'll have used the unit circle. Most teachers teach this with the unit circle, which makes me want to throw up thinking about that unit circle. So I teach it with geometry. I look at my reference angle. I draw my pizza, or the 2 pi cut into pieces, and then I just count. And I use my all students take calculus. So here's the first problem we finally get to do today. I might ask you something like, find the sine of 7 pi over 6. Question? No? Find the sine of 7 pi over 6. So I'm going to use my first diagram there where the pizza is cut into 12, right? The whole pizza pie is cut into 12 slices. And I want to find the 7th slice. So here it, right? So everything, 1, 2, 3, yep. So the 7th slice, 1, 2, 3, 4, 5, 6, 7. There it is. This is the triangle I'm talking about. But I know sine is a y value, so this is the opposite of sine of pi over 6. I'm always trying to go to the reference angle. So the quadrant's telling me the sine, SIGN, and then the reference angle's telling me the ratio. And that's, so minus 1/2. So I'm getting the sine from the quadrant. And I'm getting the ratio, right, from the reference angle. Let's do the cosine of negative 3 pi over 4. So we're cutting pi into 4, which means the whole pizza into 8, and we're counting to the negative 3, right? So negative 1, negative 2, negative 3. Yes, you see? When I'm counting negative, I'm going clockwise, right? So cosine is an x. Is that a positive there or negative? Only tangent is positive in that quadrant. Negative, right? And so, again, this is my angle. It's got to be the bow tie angle, right? So this is a negative, because cosine is negative there, but the reference angle is just pi over 4. And I know from my chart, I've got it memorized, that that's rad 2 over 2. So the answer is negative rad 2 over 2. Let's look at that on Desmos. Cosine of negative, what did I say, 3 pi over 4? And I got the negative of square root of 2 over 2. Boom. Let me give you some problems in this section. Number 21 to 29. Really, is that it? No, I guess you could do more. Oh yeah, 21 to 63. 21 to 63. Just do them. I don't care if you hand them in. No more. I don't want any more homework. But you're doing it for yourself. You're doing it to make sure you know what the hell's going on. You want me to do one more? Good answer. So number 53, it says find the exact values of the 6 trig functions at 8 pi over 3. Find the exact values of all 6 trigs at 8 pi over 3. This is number 53. So theta is 8 pi over 3. And I want to find sine of theta, cos of theta, tan of theta, cosecant of theta, secant of theta, and cotan of theta. So first of all, I need my picture of pi, the whole pizza cut into 6. Yes, I'm always doubling that denominator. And I want to find the 8th slice. 1, 2, 3, 4, 5, 6, 7, 8. So it's this angle, this triangle that I'm dealing with here. That's my 8 pi over 3. You see it? 8 pi over 3, yes? So I want to find sine of 8 pi over 3. Well, the sign there is positive or negative. Sine is a y value. Is that positive or negative in terms of height of that triangle? Positive. So this is a positive of the sine of pi over 3. Once I figure out that leading coefficient of the angle tells me where I am. But once I know that, all I have to do is reference back to that table I gave you. Right? So this is now what? Square root of 3 over 2. And I mean, I've been doing this for a long time, right? But I want you to have it, right? I want you to have it as quick as I do before the chapter, the third test. So it means you have to practice, you have to think, you have to struggle, you have to ask for help. You can't do nothing. Cos of 8 pi over 3. What's the deal with cosine in that quadrant? Positive or negative? Negative. So this is the opposite of cos of pi over 3. Once I figure out what sign, S-I-G-N it is, all I have to do is find the ratio. I mean, look at these triangles. Look at all these triangles. Don't you think they all have the same ratio? Those 4 triangles that I'm calling the bow ties all have exactly the same shape, same size. So they all have the same ratio, but some are positive and some are negative depending on which quadrant you're in. So all I have to do is reference back to that original one, right, of pi over 3. So in here I get negative 1/2. And again, it's just I'm using that table. When you're practicing these problems, have that table out in front of you, right? Tangent of 8 pi over 3. Well, what's the slope of that hypotenuse? Look at that hypotenuse. What's the slope of that hypotenuse? Positive or negative? Negative. So negative tangent of pi over 3. Tangent of pi over 3 is rad 3 over 3. So it's just rad 3, right? Tangent of pi over 3 is just rad 3. So negative rad 3. Cosecant of 8 pi over 3. Well, this is nice because I don't have to think anymore. I already know what the sign is. So cosecant is just the upside down. 2 over square root of 3. And we usually like to rationalize. So I'm multiplying by 1 in the form of rad 3 over itself. So I get 2 rad 3 over square root of 9. So I get 2 rad 3 over 3. Is that making sense, me rationalizing? Can I get a yes from anyone? Is it making sense when I rationalize? Okay. Does anybody not understand what the hell I'm doing when I'm doing that? So I got this answer, and this is something that usually wants to be rationalized, meaning I don't want an irrational number, square root of 3, in the denominator. So I multiply it by 1 by whatever irrational number I have in the denominator over itself, and that will that'll make it rationalized. Yeah, no, it's just like an ancient system of numbers. So, but when I have an irrational number downstairs, I want to rationalize. What about the secant of 8 pi over 3? Well, that's just the ratio of cosine. Upside down, right? The inverse of, reciprocal of cosine, so it's just -2, right? And then the cotangent of 8 pi over 3. That's the reciprocal of the tangent. So -1 over square root of 3. And again, I'm going to rationalize with rad 3 over 3. Sorry, rad 3 over rad 3, which is negative rad 3 over square root of 9, which is minus rad 3 over 3. I know, torture. It'll get a little bit better, I promise. All right, have a great day. I'll see you Monday. Have a great weekend. Get some